All right, let's dive deep into something that's really foundational for LLMs, tokenization. Because if you're training a model, or even just using one, you should know they don't actually read text, not like we do.
No, not at all. What they're really seeing is just a long sequence of numbers, integers. We call them token IDs.
hmm
And tokenization is that crucial first step. It's the process that turns your text into those numbers the model can actually work with.
The language of the machine,
Mm,
essentially.
exactly. And the main goal of any good tokenizer is really compression. You want to pack as much meaning as you can into the fewest possible tokens.
Right, because fewer tokens means less compute.
Yeah.
And more importantly, you can squeeze a lot more useful information into the model's context window before you hit that hard limit.
Absolutely.
So that's our mission today. We're going to unpack the huge redesign in Transformers V5. Hugging Face basically decided to take tokenizers from these, mysterious black boxes and turn them into architectures you can actually inspect and even customize.
To really get why this was such a big deal, you have to understand the old pipeline. It's not just one step, it's more like a sequence. First, you have a normalizer cleaning the text, then a pre-tokenizer does some initial splits, and only then does the actual model algorithm like, say, BPE or Unigram kick in to do its work.
So it's a whole assembly line. And I know there were two main architectural layers, right? You had the super fast, Rust-based tokenizers library doing the core work.
That's the engine, yeah. It's language model agnostic, just pure speed. But on top of that, you needed the transformers library wrapper, which is in Python. And that adds all the model-specific intelligence, things like padding, truncation, applying a chat template, adding special tokens.
Okay, but hang on. If that Rust backend was so fast and so solid, why did everyone complain about the V4 implementation? Why was it such a nightmare?
It was a maintenance disaster, plain and simple. The biggest problem was opaqueness. In V4, you couldn't just load, say, a llama tokenizer and easily see how it handled whitespace or even what core algorithm it was using. That information was completely buried.
It was a black box.
A total black box. And worse, for every single model, they had to maintain two parallel implementations. A slow one written in pure Python and the fast one backed by Rust.
Wait, two separate code bases for every tokenizer.
For hundreds of models, it meant huge code duplication, constant bugs where they wouldn't behave identically, and just a massive amount of technical debt. It made building a new tokenizer almost impossible for a normal user.
Which brings us to the big philosophical shift in V5, and this is the part I really love. They separated the concerns. Tokenizers now work a lot like a PyTorch NN module. You have the architecture, the rules, and the pipeline. And then you have the trained vocabulary, which is like the learned weights.
And that separation gives you immediate wins. First one is transparency. A V5 tokenizer, like Gemma Tokenizer, now just explicitly declares its structure right there in the class. You can instantly see it uses BPE, you see its normalization rules, everything. The black box is gone.
And the second big win has to be simplification. That whole slow versus fast mess is gone too, right?
Gone. It's consolidated into one single file per model. And the fast Rust backend is now just the default. It's so much cleaner for everyone.
Okay, and the third benefit you mentioned.
Trainability. And this is, I think, the coolest part. Because the architecture is now separate, you can instantiate the exact blueprint of, say, a Mistral tokenizer, but with no vocabulary, just an empty shell. And then you can call a train function on it with your own custom data.
That's incredible. So you're training a brand new vocabulary, but you're guaranteed to keep the exact architectural DNA, the normalization, the processing.
Yeah.
Everything the parent model expects is preserved.
That's a perfect way to put it. The DNA is preserved. So V5 really delivers three massive improvements.
Yeah.
One file per model, a visible architecture, and these natively trainable templates.
But the wrapper is still key.
Oh, absolutely. The Transformers wrapper is still essential. That's the layer providing all the crucial model awareness handling context length,
Right.
inserting the chat prompts, and, getting the final batch ready for the GPU.
So let's bring this home. What does this all mean for you, the person who's actually trying to get an edge on a project? This ability to train a custom vocabulary while perfectly preserving a model's architectural DNA, that opens up some really interesting doors. Think about it. What if you trained a model-specific tokenizer only on a highly specialized data set, like, say, your company's internal medical research? What kind of hidden knowledge could you be compressing into fewer tokens that the general public model completely missed? Something to chew on for your next fine-tuning job.